Hey, hello there. So today I'm talking about the single number question, 137, which is a follow-up to 136 single number. So just gonna spend like 2 minutes, 1 minute, quickly refresh the approach to 136. The question is as follows. We have an array of integers. Every element appear twice except for one number that appear only once, and we need to find that number. So the property of this problem can be solved effectively with the exclusive OR operator. If we do exclusive OR between the same number, we cancel each other out, we get 0. Exclusive OR between 0 and any other number is that number. So if we do this by using an accumulator with this exclusive OR as the accumulation operations, then the numbers that appear twice will cancel each other out to reduce to 0, and we left us with the single number exclusive OR with 0. So in the end, the accumulator will be that single number. So that's the approach to this question. The follow-up 137 single number 2 is that we still have an array of integers. Every element appears 3 times now, except for one number, which is appear exactly once, and we need to find that number. So it's a lot harder compared to 136. I guess if we have that the solution in 136 in mind, we can kind of reason through that on an individual bit position level kind of perspective, because thinking in whole number is going to be a lot difficult when we have 3 repetitions. So let's think that on a single position bit, let's say it's the i's position, with a single accumulator, right? So that's what's this? I call it res. So let's just call it res. Initially, you will have a 0 at that position, and the first time we see a number that has a 1 bit in there, we flip this to be a 1. That's done by exclusive OR, right? So it's res exclusive OR some number, and the second time we see the same number, or it could effectively be some other number with the 1 bit at this position. So effectively, just for the simplicity, we'll just call it we're doing exclusive OR again with this number x that has a 1 bit at this i's position. Then the result variable here at the i's position, the bit gonna be turned from 1 back to 0. And the third time, it's the single number that has this has a 1 bit at this position. Let's just assume that's the case. Then we're gonna turn this bit to be 1 again. We could have some other number that appear twice. Let's just call that number z. Fourths and fifths, it's gonna be 0 and 1. So this is at the individual bit position level, how this exclusive OR accumulator solution works. It's basically that the number that contains a 1 bit in that position, because most of the elements are going to appear twice. So it's turn it into 1 and 0, 1 and 0, 1 and 0. Only that the single number, if it has a single bit at that position, it's going to turn this position in this result to be 1, and that's the only one that counts. So we have this pattern that it go from 0 to 1 to 0 to 1 to 0 to 0 to 1, and this is effectively the it's telling us the so if it's a 1, it's actually telling us that's the odd number of times we see a 1 bit at this position. If it's 0, it's telling us it's the even number of times we see this a bit. So similarly, when we're dealing with this follow-up question, it's now three elements now. We can think now 1 accumulator is obviously not enough, because with 1 accumulator we have just 0 and 1 at each position. It's not going to be able to tell us which number appeared 3 times, we need at least two things to tell us. So it will be one accumulator that's telling us the first time out of 3 times we see it, and the other one is going to be 2 out of 3. Let's just call this 1 and 2, first or second. And initially they're going to be at the i's position. I-T-I-E-L. Initially these two accumulator at the i's position are going to be 0 and 0 for the first time and second time. Then what we do is actually do some operations on numbers. Maybe like 6 sevens. So let's say that we are doing exclusive OR with x for the first time, for the second time, third time, and then we have y. Let's just simplify this a little bit. X, and z is now the let's just be I should plan a little bit better. So the first time we see x that has a 1 bit at this position, we want to turn this bit on, and this second bit here, a second accumulator, should remain unchanged. And the second time we should turn the first off and turn on the second. The third time we should make sure that both of these are off. The fourth time we effectively back to the initial state here. So basically this two accumulator, after 3 times we see 1 bit at that position, we have to go back to the initial, and then it will just be repeating 1 0 0 1 and 0 0 1 0. So in the end, the elements that appear 3 times will if they have a 1 bit at the i's position, they're going to be cancelled out to have zeros in both the first and second accumulator. Only when we finally encounter a single number that has a 1 bit in the position, we can effectively just looking at the first accumulator. It will be it will have the right bits at the right position to tell us what the single number is. So with 2 accumulators, we can solve this problem. The problem is the prior update rule is quite simple. We just do the single accumulator exclusive OR with the whatever that number that comes in. Here it's a little bit difficult, but the thing is it's kind of a finite transformation we can do. If we see a 1 bit, there are only 3 changes, from 0 0 to 1 0 and 0 1, from 1 0 to 0 1, from 0 1 to 0 0, back to 0 0 again. So in the worst case, we'll just hard code this transition rules instead of finding some smarter bitwise operation formula that works on the whole number. If we couldn't reason through that and find that in interview time, I guess it would not be a bad idea to actually just code this 3 transition rule and do that for every position. So I'm actually just gonna code this up because it's actually my first reaction to this problem. So we're just gonna have a 32 bits accumulator. Initially it's gonna be 0. We have a first and a second, 32 and the 0. What we're gonna do is to throw a double loop here. For every number, we're gonna flip the bits at the possible positions. For the 32 positions in the number, we're gonna try to apply the update rules for the bits. So the table here, I'm just saying that every number has a 1 bit in the position. Then we need to do this transition. If it doesn't have, then the accumulator value at that position should be unchanged. So So we just grab that bit, which is equivalent to shifted the number towards right by the amount, and then do an AND operation with 1 bit to check whether the number has a 1 bit at the i's location position from the right. If we do have a bit, then we need to do some updates. The condition is that if first is 0 and the second is 0, we would transfer that into 1 0. So we're just going to come up with code up a sort of like the most straightforward brute force condition here. Then we're gonna turn on the first, because it's we haven't seen it once, we haven't seen it twice. It's a 0 time. We have seen it 0 times. Then we make sure that we flag it's the first time. We inside this cycle here, inside a period, a cycle of three transitions that we see this. We make sure we flag the first. Oh, sorry, it's not A and B. It's first and second. Okay. And then it's the second. If we're in the second state, which means it's the first out of the 3 times we see a bit, 1 bit at this position, then we transform into the third, the first state, the second state, the third state, which is it's not our first time seeing this 1 bit at this position, but it is indeed the second time we see a 1 bit at this position. That's what the 0 1 here is saying, which is else if first is 1, second is 0. And what we do is to make sure that we turn off the first and turn on the second. Lastly is this from the second to third. If it's indeed in our second time seeing this number immediately prior to this time, then it's in our third time. Since it's in our third time, we actually turn off the first and second. Make sure the first and second are all off. So it's like a dummy encoding for categorical variables. We need a 1 less variable than the actual number of levels. So we have a 1 and 1 to 3, 3 different times. Initially it's basically 0, 3 as well. So I guess we need a 2 to count for 3 different. It's basically just we need 1 less. I'm not sure if that makes sense to you. So if it's not our first, but it's the second, then we make sure we turn off second. So this is a very brute force position by position bit state update code in a very nasty double loop here to solve this question. So by the end of this for loop, we processed all the number. For every number, we updated the position by position in the binary kind of representation to deal with this transition table here. So in the end, we should be able to reconstruct the single number using its binary representation, which is now in the array form in this variable first. So we're gonna have a number, have an integer to be 0 here, and try to reconstruct the number. So it's basically for int I from 0 less than 31 and increment, because the why it's become 2 lines when I guess I'll just make this 2 lines then. Okay, it looks nicer. So what we do is to reconstruct the resulting number. The 31st position is going to be the sign bit, and if it's a negative number, we're actually going to treat zeros as ones, and after that we're going to do a complement. If it's the sign bit is 0, we're going to treat ones as ones. So we pretty much just going to increment the result by 2 to the power of I, which is equivalent to shift this 1 bit towards left by I position. So the condition is that if the current bit it's the opposite as the sign bit. That's equivalent of saying by doing an exclusive OR with the sign bit 31, then we increment we add 2 to the power of I to this result. In the end, we should return based on the sign bit. If the sign bit is a 1, meaning that it's negative, then we have to do a negation, do a complement of the result here to make sure it become the positive number multiplied by -1 and subtract 1. Otherwise, it will be the result. So that's I think this is the correct way of reconstructing the number from its pure binary representation, position by position. So let's try to submit this one. Yeah, it's working. It's not particularly fast, but the time-space analysis, let's do a little bit of that. The time is this is an order of n with n number, and we have 32. So it's 32 multiplied by n. That's now a time. And if we consider 32 to be constant, then it's a linear time algorithm. For space, we have 2 arrays of size 32. So that's just the order of 64. It's a constant in space. So it's a constant space and linear in time, which satisfy this requirement here. It's extra is basically just asking constant memory. So I think that this kind of a crude way of handling the bit transitions accumulations can be a reasonable solution in actual interview time. Let's just do a little bit optimization about this logics here. So we find that in this second branch is doing 2 things, and let's analyze it a little bit. So bit is 1. That's only case when we do this updates. So let's make this logics a little bit nicer. If bit and what? If bit and let's just look at some common patterns here. Second is 0, second is 0. That means second is on the opposite to bit. What do we do? Here, first is 0, we turn it to 1. Here, first is 1, we turn it to 0. It's equivalent to, in this 2 branch, where second is 0, we effectively turning first to be the opposite of whatever value it is, which is effectively doing an exclusive OR with bit. So, exclusive OR. And then look at the second and third condition. What we do here is to second is 1, we turn it to 0. second is 0, we turn it to 1. So that's change this, and the condition here is here if the first is 0, when you do exclusive OR with bit, it will be 1, so that will enter this here. If the first it's 1, after this if condition, you will be already turned to 0, so you will fall back to this. So I'm just gonna swap this, and we end up with a simplified condition for this, rather brute force code to handle the bit state accumulator state updates. So it will become something look a little bit nicer, but it doesn't really reduce any kind of time and space complexity. It's just a nicer way of wrapping up this update rules. The thing to think about now is we didn't really look at the individual position kind of level bit, how the bit transfers updates. When we look at the first single number question, we look at the whole number kind of perspective, which is equivalent to, say, it's kind of doing the vectorized operations. And here we here it's just because I think it's a little bit difficult to reason through on the vectorized version, the whole number kind of level. That's the reason I go deeper into go to a little bit low level to look at the individual bit position level, how the update looks like. So since that we now have this, we can start to, I guess it's first it's a working solution, and it's in terms of time and space is quite optimal. Then it's the opportunity to try to think about if there are any way we can do vectorize the version of this. It's going to be looking at this simplified formula, which is saying that if we try to translate it into this two logics into English, when would the second and bit exclusive OR bit be 1? That's when we have a 1 bit, and it's not our second time of seeing this bit. That's equivalent of saying if it's not this initial or first, and then we see a 1, we should make sure we turn on the 1. That's not the second time. So yeah, basically it's the second time flag it's off, and we indeed have a 1 bit. We make sure we set the 1 bit to be on, and here the second time we actually see this 1 bit when we're executing this line, it is saying, yeah, it's still not our, as far as we know so far, it's still not our second time seeing this. Then we do this exclusive OR, it's going to turn this off, and then it's then the first will become 0. So then it's actually the first time we can update the second. Yeah, it's a little bit tricky, but it's basically saying not second. We make sure that we flip a 1. So you go back to this simple prior question. We always just alternating between 0 and 1, 0 and 1, 0 and 1. So whenever the second position flag is not on, we do this alternating pattern. When it's when it's indeed the second time we encounter this 1 bit of this position, we will no longer resume that 0, 1, 0 pattern for the first accumulator. And when the third time, we just make sure it's all off. Yeah, so the logic is basically, if it's not second, then first we do the exclusive OR update. That's the alternating 0, 1 position. And if it's not first, for the second we actually do the alternating position. We change 1 to 0 and 0 to 1. No, the second logic is not right. The only case that we update the second to 1 is when second is 0, so that when it's doing exclusive OR, it will be turned on. But first is actually on. First is actually off. First is off. So that's first is off and second is off. Yeah, that's right. That's the similar to this here. It's going to be two continuous update rule. It's not as this three statement here. It's going to be parallel. So what it should look like. So we're going to have to vectorize the accumulator now instead of this position by position, individual position level accumulator. So we're still gonna just enumerate with over the number ones, and the way we update the first is that if second is not on, we do this alternating change 0 to 1, 1 to 0, yeah. If second is on, we don't do any kind of a update. Then second become off again. Then we go back to the alternating 0 1 0 update rule. So it's a complement of second. Do an AND operator with first exclusive OR with the number. This first exclusive OR, it's just this pattern here. We apply this pattern only when the second is off. The update rule for the second is going to be something and second exclusive OR with this number. And that is when first has been turned off in the same iteration. So it will be here, not first, complement of first. And in the end, we should just return first. It will be done. So this is a much simple but code, and it's actually vectorized operations for essentially the logic here. But it would be hard to directly come up with this, I think, unless somebody who is really comfortable in thinking in that way. Otherwise, I think coming up with something like this should be okay, and actually shows the understanding of about how the bit manipulation works. But this is not one of the solutions this solution tab shows. This is my first time trying to solve this. This is what the code that I come up with. So yeah, so I guess, but when you do analyzing the code on the individual bit level and try to think about how to make this into the vectorized form, this does help you to really reach this really elegant code here. Yeah, so that's the question today. Let's just submit this to see how faster it is compared to the manual bit by bit, essentially the same code as this. Yeah, it's much faster, vectorized computation. So yeah, that's the question today.